What's up, people? What's going on? I'm waiting for everything to come online with the streaming. I'm streaming across all these different platforms. And today we're doing another coding challenge live. This time I'm doing a medium, my first medium, validate binary search tree. So we're going to see how this goes. I've done this one before, but that doesn't mean much for me because you never know what'll happen in real time. Thanks for joining. If you have, please share, like, follow, subscribe on what channel you're on if you want to see more content like this. And let me know what you think about the problem and the solution I come up with and any tips or anything like that. But without further ado, I'm going to jump into it. So the problem today is called validate binary search tree. It's a medium on Leetcode.com, and it goes as such. Given the root of a binary tree, determine if it is a valid binary search tree, a BST. A valid BST is defined as follows. The left subtree of the node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. And both the left and right subtrees must also be binary search trees. So it goes on to give a couple examples here. This is 2, 1, and 3. And as you can see, am I missing? Oh yeah, as you can see, 1 is less than 2, and 3 is greater than 2. So the left side of the tree nodes are smaller than, as it goes from left to right, it's smaller. So the subtree on the left is smaller and the subtree on the right is larger. In example 2, the subtree on the right is smaller here, so that's valid subtree. On this subtree, 4 is smaller than 5. It should be greater than 5, so that's incorrect already. And if you look here, 3 is less and 6 is greater than 4, so this is valid subtree, but since this is invalid right here, then the whole tree is invalid, so you get false. And here you get true. And then some constraints down here. The number of nodes in the tree is 1 all the way to 10 to the 4th power, and then the node value is between this range, so you can't have a negative node at -2 to the 31st power. So I'm not sure how much these will affect the problem, but good to know and good to ask about if you're in an interview setting. So let's get to the core of the problem. If I was in an interview, or if I was just trying to figure this out on my own, what would I be thinking if I didn't know the solution to the problem? First of all, I don't see how you get a way around this without knowing how to traverse a tree with code and knowing the objects, like how a tree node is built and how a tree looks like in code. So that's something you just have to go study on your own. I don't see how you can do this problem without it. You may be able to you may be able to figure it out if you're just good with objects already and you know how a value for a tree node and then its left and right legs for a BST, because it's just gonna have a left and right, only 2 legs on each node. And you may be able to just figure it out, but I suggest you go through and learn how to traverse a tree with code, how to go from this node to this node to this node, how to do a depth first search or a breadth first search, because without that it's going to be hard to solve this. But if I'm just trying to solve this in my mind, it's usually what I try to do and talk through it like just thinking. I would want to check at each node that I traverse when I get to the node. So let's say I get to 2 here. I want to check that this child is less, this left child is less in value than my current node that I'm on, and then the left subtree here, the right subtree here is greater than the node that I'm on. But furthermore, I want to know that the whole, like when I'm here, I want to know that this whole subtree is, all the values in this subtree are greater than 5. When I get here, I want to know that all the values all the subtrees of this are less than 1. So as I go, or as I go to left and right. So I want to know that, like when I'm on 5, that all the subtrees here, all the subtree in general is less than 5. And then when I get to 1, I want to know that the left is less and the right is more. But the issue, kind of complication with the problem is, like, if I get to 4 and then I go to 3, 3 still needs to be greater than 5. And that's why I think the tricky part of this problem is. So even if, let's say this was 6 and let's say this was 7 and this was still 3. So I get to 5 and then I get to 6 and I say, okay, yeah, 6 is greater than 5. And then if I go to here and I say, okay, 3 is less than 6, then I'm like, okay, this is fine. But what I didn't check is that if 3 is greater than 5. And that's basically the issue there with that. So basically how you want to solve this problem is you want to do a depth first search, basically, or not even it's kind of a depth first search, but it's kind of like a pre-order traversal of the tree. It's kind of like, to me, mixes in with like how you do a depth first search, but I'm not sure the exact term for how you would solve this problem exactly. But you basically want to traverse this tree from node to node. You want to look at the left node and right node, or left like leg or whatever, and right leg of each node that you come to. And as you get to a node, you need to pass the state of the maximum. And even, like, to just explain it first before you do it, like when I get to 3 here, I need to know what the minimum, or what the max is that I need to be greater than, or the minimum that I need to be greater than. So here I know that no matter what on this side of the tree, I need to be greater than 5. So I need to keep, even when I get here, I need to have state of this 5 here. Like, I need to make sure that I'm still higher than this 5, even though I'm less than the 3. So if you think about it in that way, the trick to the problem is that you need to keep state of the, when you're on this side, you need to keep state of the min and max, and then on this side you need to keep state of the min and max, and your min and max will depend on which side of the tree that you're on, or which leg you're currently looking at. So let's jump into it. Hopefully it makes sense when I jump into it. This one's, it's a medium, so it's a little bit more hard to explain, do, but I'm gonna try to get through it the best way I can. Hopefully I can. So valid BST. So the first thing I want to do is I want to make a separate function is valid, because I want to start doing a recursive call, which is when you do a depth first search, or when you do like a pre-order traversal. When you traverse a tree, you have to go to your left and right legs of the tree. And so doing it recursively is typically how you would do it. If you're doing a breadth first search, you could do it with a queue and do it iteratively. But in this case, I think you can solve this problem both ways. But in this case, I'm going to use depth first search, basically. And so what I want to pass in here is the current route that I'm at. And I also want to pass a max, or maybe a min and a max in here as well. And so how you want to think of these problems, and one thing I'll jump backwards to is, like, what does a tree node look like? And so basically a tree is simply a group of objects that each node has a value, each node has a pointer or a left and right pointer to its object. So val here would equal 2 for this one, and then left and right would be these objects nodes, which each also have their own left and right. So in the interview setting, I'm not sure. I've been in different settings where they've given this object already. I've been in settings where you had to create it yourself. But either way, you kind of need to, like I said before, you kind of got to know how a tree is structured in code, so you can either create it or know how to use it when you find it. So getting back to the code, is valid. So this is my main function, but what I'm doing is creating a recursive function here, and I'm going to use it in this function once I figure out what the heck I'm doing, because I'm actually just doing this from my mind. I'm kind of like blanked out on what I'm supposed to do. But this is like the fun of it, doing it live. Like this is if you want to call it fun, I'm doing it live, and so I'm trying to figure it out as I go, even though I've like forgot what to do. But that's cool. But the first thing I usually know is when I'm dealing with a tree, I already have in my mind that what happens, the edge cases. What happens when I get to 1 and then there's no left and right leg, or and so then when I get to those points, the root is going to be null. The left and right legs are null. So you kind of have to, when you think about these problems, you have to kind of think about these recursive functions like from the viewpoint of a node itself. What all do I need to do on each node? When I pass a node through here, no matter where it is, what do I need to do? Well, the first thing I need to do is check if it's null, because I can't do anything with it if it's null. It doesn't have a value. It doesn't have a left. It doesn't have a right. So if it's null, in this case, if it's null, is it a valid binary search tree? Yes, because there's nothing. It's nothing. So you can go ahead and return true for that. And then next, I want to basically, if I'm doing a pre-order traversal, and that's something that you might have to look up too, but basically what that means, and hopefully I'm using the right term, pre-order, is that you're going to look at the node you're on first, its value, then you're going to start looking at the left, and then you're going to look at the right. And so the next thing I want to check then is the value that I'm currently on first. So I'll basically want to check the validity of the current node I'm on. So I have my min and max passed in, but I want to check if the root value is, if the min value is, if the root value is greater than the min that I passed in, and the root value is root value is less than the max that I passed in. So basically, if I know if root value is in between max and min, then I know that this is a valid tree. So I think I can return true here. And then lastly, I want to look at, based on how I'm traversing the tree, going from the middle to the left and the right, I want to look at the left and right values of the tree. And I basically want to go recursively now, passing in the root again, and I'm passing in a min and a max, and I'm going to fix these later. And actually here, I actually think I need to reverse this now that I'm thinking about it. I need to basically say, I need to return false here. So I need to find out if this is outside of the range. So if, because I don't want to get down to here, if I already know that this value isn't in the right range that it should be, then I should go ahead and return false. So I want to say if root value is less than min, I wonder if it should be less than or equal to. So what does my problem say? Only contain nodes with keys less than. So it has to be less than. So if the root value is outside of my range, if it's less than min, now I'm going to return false. Or if root value is greater than max. And I might need to fix this. I don't know if it's greater than equal to, less than equal to, or if it's just greater than and less than. But I'm going to try to test that later. And then here, so when I'm looking at my left and right, as I have my min and max, what I need to figure out is when I'm on the left, so this is supposed to be left, and this is supposed to be right, because I'm going to now look at my left and right. I'm going to come back into this function recursively with the left and right and a new min and a new max. So when I'm on the left side of the tree, basically whatever node that I'm on is now my new max. Like I can't have something on the left side greater than this value. Yeah, I can't have something on the left side greater than this value. It's got to be less than. So the new max is whatever. The new max keeps getting lowered every time I go left, 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 left. So here, I need to make my new max is root value. So whatever I'm on right now is now my new max for the next time I come in here with the left tree. And so now when it does the comparison here, it's going to do a comparison against this new root value as the max. And it can't be greater than this. And so, yeah, if this is less than, I'm trying to think if this is less than, yeah, if this is less than or equal to, then yeah, I need to break out. So I think this is less than or equal to, because it can't be equal to, it needs to be less than. So if it is less than or equal to min, or it is greater than or equal to max, then I need to return false. And then here I return, I set root val as my new max. And then when I'm on the right side of the tree, my minimum is going to be whatever this value is. So my minimum is going to keep increasing as I go to the right side of the tree. So every time I get to a node, it's going to become the new minimum. So here 5 is the new minimum. So this needs to be greater than 5. Then when I move here, this needs to be greater than 4 or whatever this is. And then even when I get here, I'm going to have a new max of 4. But then when I go this way, my new minimum is going to be 4. But then my max is still going to be this. It's still going to be whatever I carried along through this. So, which would have been 5 actually. So that's kind of how this recursive function works. So when I get to this side, actually my minimum is going to be the root dot value, and my maximum is just going to stay the same as whatever I've been passing along before. Sorry, something went off in my house. But yeah. And so then here, how I use this function here, which usually people would do first, but I kind of think backwards. I kind of think backwards from the solution, so I know what the heck is going on. But I know I need to return if this root node is valid, And so now how do I figure out what my min and max is? Well, when I'm at the top here, my min and max is like the least and greatest thing possible in existence. Like it's actually like an incredible, like an impossibly high number. It's infinity, negative infinity for minimum and negative and positive, because it can be anything because this thing has no parent. So it's just a way to make the program work. But I need to, in JavaScript, I think I can use number, negative infinity, and then number positive. And this will be different in different languages. And you can also do this a different way. You could like just make these 0, and then you can add some condition here to say if it's 0, then just don't even worry about it. But I don't like doing that because like what if these numbers are negative, and so it just kind of, I just like rather use negative infinity so that like even negative numbers can't be less than this number. And so this looks right to me. The next thing I probably want to do is kind of like try to trace my code. Recursive code is really hard to trace for me. So I'm gonna go so what I do usually is take all my variables and track them as I'm running through this. So I have the root, and then I'm gonna like whatever my new root is, and then whatever my min and max is at the time, and that's how I'm gonna track this, because otherwise it's really hard to track. So I'll at least be able to track when things go bad. And then I'm gonna try to put a tree in here. How can I do a tree? Let's say 2. Where's the 2, and then this, I probably would never do this in like real life, but I'm trying to do this to explain it. This is 2, 1. Dang. So this is my little bootleg tree here. 1 and 3. So when I come into this function here, I'm going to come in with 2 as the root, and it's going to go into this recursive function with negative infinity and positive infinity. So this is like negative. I don't even know how to put that. It's going to put like super negative, super positive when these come through here. So nothing can be lower than this, nothing can be higher. And the root is 2. So now I'm going to get into here with root 2. Basically, this is not equal to number 2. This is like the object, the node 2. But I'm just putting 2 so we know which one we're talking about. So then I get in here. Is it null? Return true. No, it's not null. So I'm going to skip this. Is root value 2 less than min? Or is it greater than max? No, because 2 cannot be less than negative infinity or greater than positive infinity. So I'm skipping this state 2. And now I'm going to jump down into this logic. I'm going to go this way first because I'm going in a pre-order traversal. So then I'm going, now I'm going to go into the loop again. I'm going to go into recursive function again, this time with left as my root. Left is 1. So this is left. And then min is still going to be negative infinity still. And max is going to be actually the old root 2, which I came from. So then I'm going to come back into this again with these new values. Is root null? No. So is root value, the new value is 1. Is it less than or equal to min? No, because it can't be less than negative infinity. Or is it greater than or equal to max? No, it's not greater than 2. So we're skipping this and we're going back into this function again. And this time when we're looking, I don't have to go over there. Sorry, I wrote it here. This time 1 doesn't have any children. So this is going to be null and this is going to be null. So I can kind of skip, I can kind of figure like in my head what's going to happen when these functions go in with the value of null here. I don't have to worry about the rest of this. I know when I come back into this with no, I'm going to instantly return true. So I know this is true and true. So now I'm returning back up. I'm going backwards back up to this 2 with a value of true. And so now I'm at 2, and I'm kind of like, that's why recursive functions is so hard to do, because now I need to process the right side of the node 2. So now I kind of like backtrack up to 2, and then the max is back again to this, because now I'm back up to like my root. And then when I go in with, now I'm going to go in with 3, and because I'm on this side of the value 2. This is really hard to explain, but this is recursive functions. There's really no other way to do it, as far as I know. So this would be 3, and then I'm gonna put, since I'm on the right side, my new minimum is whatever 2 is. Like nothing over here on this side can be less. It has to be greater than 2. So now minimum is going to be 2, and max is going to stay the same as what it came in as, which was positive, like infinity. So then I'm going to loop back in here. Is root equal to null? Null is value less than min. Value currently is 3. Is it less than the min? No, it's not. Or is the value greater than maximum, like, which is like infinity? No. So I'm skipping this. And then I'm going to hit this. And then I'm going to see that I have no children on 3. So I know that this is going to be true, because I'm going to hit this for both of these cases. So I'm going to return true back up to 2. So I'm going to backtrack again back to 2. And then this is negative infinity again. And I got true for this the first path I went down. And I got true for this the last path I went down. So now I return out to back to here, and I return true, which is the answer for the input of like 2, 1, and 3. And so I can do a negative example. It's probably better to do a negative example here to cover the cases when it doesn't work out. But I'm going to try to move forward without it so the video isn't too long. But typically, and then if you're not in an interview, you have all the time in the world to do this. But if you're in an interview, you got to kind of be fast. So like you kind of got to pick and choose what you decide to do before you just try it out. You're really just trying to show the interviewer that you even can do that, and that you can, because sometimes you won't have anything to run. So you actually have to do that. But I'm going to go ahead and run it since I do have a runner. All right, so I got the correct answer for 2, 1, and 3, which that was this thing over here. I can't believe it worked on the first try. And what Leetcode allows you to do is put in different inputs. So I'm going to put in this bad tree, which is supposed to give false. I'm going to test it out by changing the test case in Leetcode. You can do that right here. Change it from 2, 1, 3 to this. And I'm going to run and see if I get the right answer. All right, cool. I got it, because I didn't know how this one was going to go, because I was definitely blanking out there. I don't know if it seemed like it, but I definitely got stuck because in my mind, I didn't know what to do. But eventually I figured it out, that's why we do these type of things. Because if you doing this in the interview, it's going to be under pressure. But I'm not doing this to say you have to do it in the interview. You might be just doing this for whatever reason you're doing it within your job or whatever. So yeah, it looks like this is working fine. So I'm going to submit it to Leetcode to see what like my overall performance was for it, which it was alright. It's only faster than 40%. I like to be 80%, but I don't know. I don't care if I can't. If I look at the solutions and I can't find anything better than the solution they have there, typically I'm not good enough to be trying to find solutions that no one else found in the world. I'm not striving to be that good. And if you see here, if you look at the solutions on Leetcode, I'm hoping this is one of the solutions. This one's intuition. No, that's wrong. So this is the first approach, recursive traversal. So I think this is what I did. Recursion compares the node value, which is upper and lower limits. So they call them like limits. I call it min and max. Call it upper limits, lower limits. And it's basically the same thing. You get in here, you check the node itself, you check if it's outside of the limits and return false, and then you look at the left side, or you do a recursive call to the left side, recursive call for the right side, and then you pass in your new min and max based on that information. And then in your main function, you need to call, so they use null. Oh, see, so they're checking null here, right here. So I like mine better because I'm like, I don't know, I just like using the positive and negative infinity better. So this logic is a lot cleaner. If you see here, they had to do like sub condition here, or, and then this whole sub, like it's just more complicated. And then that kind of complication can kind of like screw you up, in the interview. You get confused. So anyway, I hope this made sense. I know this is a hard one. Trees are hard. Recursion is hard. I call that depth first search, but maybe that's not what that is. They don't seem to be calling it that in the solution, but that's what I call it. I don't know. I guess it's pre-order traversal. I don't know. Whatever. Let me know if you have any questions. Let me know if you have better ways to do this. I had a pretty good discussion last time I did this about better ways to do it, and so do the last problem that I had. So please like, follow, subscribe, whatever channel you're on, and let me know if you want to do more videos, want me to do different videos and problems. And thanks for watching. And I'll see y'all next time.